Matter glows at its most violent just before it disappears forever. A black hole does not simply pull matter inward and consume it silently. The process is structured, governed by well-understood physics, and in most respects predictable. When gas and dust fall toward a black hole, they do not fall in a straight line. Angular momentum forces the infalling material into a disk, a flattened ring of plasma orbiting the black hole at progressively smaller radii. As material spirals inward, it loses energy through friction and radiation. It heats up. It emits light across the electromagnetic spectrum. Eventually, it crosses the innermost stable orbit and falls into the black hole. This is the standard picture. Energy is transferred outward through the disk by turbulence and magnetic forces. Radiation escapes. The disk cools slightly as it loses that energy. The matter that finally crosses the event horizon does so after giving up most of what it had. The system is lossy by design, and the losses are, in principle, calculable. The observed luminosity of an accretion disk should follow from the mass infall rate, the efficiency of energy transfer, and the distance to the innermost orbit. These inputs are measurable. The output should be predictable. For most accreting systems, the numbers roughly agree. They do not always agree. In certain configurations, the plasma immediately surrounding the innermost region of the disk radiates at intensities that do not follow from the known inputs. The turbulence signature in the plasma, the pattern of energy fluctuations across the disk, does not match what energy transfer models produce. The material appears to heat beyond what the infall rate and friction alone can account for. It glows more violently than it should, and then it vanishes across the event horizon. Something is adding energy or failing to remove it in a way the standard model of disk physics does not capture. Matter is releasing more energy than the known mechanism allows in the moments before it crosses a threshold from which nothing returns. The standard explanation for disk heating relies on magneto-rotational instability, a process in which differential rotation in the plasma, combined with weak magnetic fields threading the disk, generates turbulence. That turbulence redistributes angular momentum outward and transfers energy through the disk as viscosity. The model is robust. It has been confirmed in numerical simulations and matches observations across a wide range of accretion systems. It is not a fringe idea. Under this framework, the heating profile of the innermost disk region should be calculable from the magnetic field strength, the rotation rate, and the plasma density. The turbulence acts as the mechanism that converts gravitational potential energy into heat and radiation. The disk glows because it is losing orbital energy to friction, magnetic friction specifically, and that energy escapes as light before the matter falls in. The anomaly appears when the observations are taken at high resolution near the innermost stable circular orbit. The plasma turbulence signature in that region carries more power than the magneto-rotational model predicts. The fluctuations are faster, more energetic, and structured differently than simulations produce. The disk is not merely warm from friction. Something in the infall heating loop is amplifying the energy output in a way that the known transfer mechanism does not explain. Attempts to resolve this by adjusting model parameters run into a structural problem. Increasing the magnetic field strength in the model to match the observed output produces turbulence at the wrong scales. The power spectrum of the fluctuations shifts, but not in the right direction. Increasing the plasma density introduces instabilities that are not observed. Adjusting the geometry of the innermost disk region moves the predicted emission profile away from observations rather than toward them. The model can be tuned to match one observable, but matching all of them simultaneously pushes the parameters into physically implausible ranges. The heating loop in the innermost disk region may be driven by a process that the current model does not include. One candidate is magnetic reconnection at a rate and scale not captured by standard disk models. Magnetic field lines in the plasma can snap and reconnect, releasing energy rapidly at localized points. In the inner disk, where field lines are highly compressed by the geometry of the orbit and the proximity to the black hole, Reconnection events could release energy faster than the magneto-rotational mechanism distributes it. The plasma would spike in temperature locally, producing the observed turbulence signature without requiring a revision to the overall energy budget. Magnetic reconnection is not a hypothetical process. It occurs in solar plasma and has been directly observed. The question is whether reconnection at the scales and frequencies required to explain the inner disk heating is physically achievable given the conditions near a stellar mass black hole. The magnetic field geometry in that region is partially constrained by observation, but the reconnection rate depends on plasma resistivity at extremely high temperatures and densities, conditions that cannot be reproduced in a laboratory and are difficult to model without simplifying assumptions. Simulations that attempt to capture reconnection at these scales require spatial resolution that current computational resources cannot sustain across a full disk simulation. The reconnection hypothesis explains the energy anomaly in principle. It does not explain the specific structure of the turbulence signature. The pattern of energy fluctuations observed in the plasma is not random. It carries a characteristic time scale, a periodicity in the power spectrum that appears consistently across multiple observations of different accreting stellar mass black holes. Random reconnection events would produce a turbulence signature with a different statistical structure. The observed pattern suggests a coherent process, something cycling through the in-fall heating loop at a regular rate rather than firing stochastically. A second candidate invokes the ergosphere, the region outside the event horizon where space-time itself is dragged in the direction of the black hole's rotation. In a rotating black hole, this region extends beyond the event horizon and intersects the inner disk. Plasma moving through the ergosphere can, under specific conditions, extract rotational energy directly from the black hole through a process called the Blandford-Znajek mechanism, which involves magnetic fields threading the ergosphere and channeling energy outward along the rotation axis. If a version of this process is operating at the disk's inner edge rather than purely along the jet axis, it could inject energy into the infalling plasma in the plane of the disk rather than perpendicular to it. The plasma would receive an additional energy input that has nothing to do with friction or turbulence generated by differential rotation. It would be receiving energy extracted from the black hole's spin itself. The Blandford-Znajek mechanism is established theory. The jet-driving version has observational support. What is not established is whether a disk plane variant of this process operates at what rate and whether it could account for the amplitude of the observed heating anomaly without simultaneously producing other observable signatures that have not been detected. A spinning black hole losing rotational energy to the inner disk would slow its spin over time. Spin evolution in stellar mass black holes has been measured in some systems, but not at the precision required to detect the slowdown signature that this mechanism would produce over the timescales accessible to observation. The process may be occurring. The current observational data cannot confirm or exclude it. Neither candidate closes the gap cleanly. Both introduce additional unknowns. The plasma turbulence signature that deviates from model predictions occurs at spatial scales and temporal resolutions near the boundary of what current X-ray observatories can resolve. The innermost stable orbit around a stellar mass black hole is small, a few tens of kilometers in radius. Resolving the structure of the turbulence at that scale requires an effective baseline that no existing instrument provides. The periodicity in the power spectrum is inferred from timing analysis of the total emission, not from spatially resolved imaging of the disk. The spatial structure of the heating anomaly remains unconfirmed by direct observation. Simulation approaches face a different limitation. General relativistic magnetohydrodynamic codes, the standard tool for modeling disk physics near black holes, must choose a spatial resolution and a magnetic field configuration at the start of the simulation. The results are sensitive to these choices. Different initial conditions produce different turbulence structures. Some produce heating profiles consistent with observations. Some do not. The fact that some simulations match the observations is not confirmation that the mechanism in those simulations is the one operating in nature. What the models agree on is the scale at which understanding breaks. The infall heating loop operates over a region less than 10 gravitational radii from the event horizon. Gravity in that region is not Newtonian. Frame dragging, redshift, and light bending alter the behavior of plasma in ways that Newtonian fluid dynamics cannot capture. General relativistic corrections are included in the best current models, but those models rely on classical treatments of plasma behavior, magnetohydrodynamics, that may not be valid at the densities and temperatures present in the innermost disk. The transition from classical to quantum plasma behavior occurs somewhere in that region. Where exactly and what it changes about energy transfer is not known. The observation and the model agree that matter arrives, heats, and disappears. They do not agree on how much heat is produced or what produces it. The event horizon is the hard boundary of this problem. Whatever process is driving the anomalous heating occurs in a region from which no information escapes once matter crosses it. The plasma carries the signature of the process right up to the point of crossing, the turbulence pattern, the anomalous luminosity, the coherent periodicity in the power spectrum, and then all of it is gone. There is no way to observe what happens to the energy budget after the event horizon. There is no way to compare the pre-crossing state of the plasma with any post-crossing state, because no post-crossing state is accessible. The heating anomaly is therefore confined to a region bounded on one side by the limits of current instrumentation and on the other by a surface from which no measurement is possible. The infall heating loop terminates at a boundary that physics can approach but not cross, carrying a signature it cannot yet explain and depositing its unresolved energy into a region from which no answer returns.